Okay, so sequences. This is the first section on sequences. So I'll show you the basics of sequences, and then I'll show you how to work with linear sequences. Okay, so before we talked about sets of numbers, and sequences are a special type of set. Sets would be a set of numbers. We would call them elements, and we wrote the elements within curly braces like this. This would be the set of even numbers up to 10, right? Under 10. With sets, it didn't really matter in which order we wrote the elements, right? So this set is actually the same set as this one. So order, these are the same. Order doesn't matter, right? These are the even numbers under 10, and these are the even numbers under 10. So same set. Now when we talk about sequences, a sequence is actually an ordered set. So sequences are ordered sets. So if we look back at this, one ordered set would be 2, 4, 6, 8. See how we leave out the curly braces? This 8, 6, 4, 2, these are two different sequences because this is the even numbers under 10, ascending, going up from small to large, ascending. These are the even numbers under 10, so not including 10, descending from high to low. Two different sequences because they're ordered sets. The order does matter. Okay. Now we need some information about how to talk about sequences. So, say we have a sequence. Let's see. Yes, let's do this sequence. 1, 3, 5, 7, 9. You see where this is going, right? And say it goes on forever. That's what the dots mean. We use those in set notation. We also use them in sequence notation. All right. We need to name these terms. If we talk about this term, we could call it the first term, or we could just write T for term 1, term 1. This is our second term. We could say second term, but we could also write T2. This one, third term, T3. Now, if we want to talk about any random term in the sequence, we could call it the nth term. And we would write that as Tn, the nth term, term n. And that could mean any term in the sequence. As soon as we give it a number, then we know what term we're talking about. But this is like leaving the number in the middle. Like this is just any term that we'll define later. Yes. Okay. Also, when we talk about sequences, there's a few ways to describe a certain sequence. You could, wait, let's write that. How to describe a sequence. We're going to talk about two ways to do that. One way to describe a sequence is like we did up here. This one is pretty obvious, right? So in this case, it was enough to just name enough terms to show a pattern. A sequence always has a pattern. Maybe I should have said that first. But in this sequence, it's obvious what happens, right? These are the odd numbers, 1, 3, 5, 7, 9, 11. And now we know how this goes on until eternity, right? So this is all we need to describe this sequence and how things are going to end here, how things are going to go from here. Another way to describe this sequence would be with an algebraic expression. Algebraic expression. Let's take this one again. 2, 4, 6, 8, 10. I'm picking easy ones because voila. Okay, I've just actually named enough terms to show a pattern, but say for some reason this would be really hard to see the pattern, we could also use an algebraic expression to describe it, which would look a bit like this. Look at the terms. The first term, T1, is 2. The second term is 4. The third term is 6. Now look what happens here. When the number of the term is 1, its value is 2. When the number of the term is 2, its value is 4. And you see what happens here. Its value is always twice its number. So if we want to describe any term in the sequence, which is Tn, the nth term, any number in the sequence is always twice its number, right? Twice its position number, this 1, 2, 3, or n. So twice its term number, its position number. Tn equals 2n. So now, using this algebraic expression, we could find any term in this sequence. Let's say we're looking for the value of the 7th term, right? Term 7. So in this case, n is 7. So its value should be 2 times 7. 2 times 7 is 14. Let's check if that's right. Term 1, 2, 3, 4, 5, 6, 7. 7th term is 14. Okay, so this works. So using an algebraic expression to describe a sequence gives you the opportunity to find any term in the sequence, however high this number is. We could now find the 250th term. Just plug 250 in here and find its value. We don't have to keep adding 2 until we've done that 250 times to find the value, right? So that's very helpful, algebraic expression to describe a sequence. Okay. The types of sequences that you're going to be working with for now are, I'll grab some yellow paper, are linear sequences. Linear sequences. In linear sequences, the jump from one term to the next is always the same. So let me just give an example that's easier. 1, 5, 9, 13. Bloop, bloop, bloop. The jump from one term to the next is always the same. What happens here? We've added 4. From this term to this term, we've added 4. From this term to the next, we've added 4. These jumps are always the same. That's why it's linear. That's what we call a linear sequence. Okay. Now to find the algebraic expression that describes this sequence, we're going to use this 4. So if a question in the book would be, describe this sequence with an algebraic expression, we know that the higher the term, the further along, the more we've added 4. Here we've added 4 once. Here we've added 4 twice. Here we've added 4 3 times. So our algebraic expression is going to have something times 4, right? The nth term will have added 4 n times. So n times 4 is going to be in that expression. That's a good starting point. Now, let's write the term positions above it. 1, 2, 3, 4. When n is 1, n times 4 is 4, right? But the value of the term is not 4. It's 1. So that's 3 less, right? The second term, n is 2. 2 times 4 is 8. The value is not 8, it's 5. That's 3 less again, right? Is it 3 less here as well? 3 times 4 is 12. 9 is 3 less. So it looks like to get to the value of any term, we multiply the term number by 4 and then subtract 3. Let's see if that works for the fourth term. Term 4. Is that in fact 4 for the n, fourth term, times 4 minus 3? Let's see. 4 times 4 is 16. Minus 3 is 13. That is indeed our value for the fourth term. So we found the algebraic expression for our linear sequence. Let's do another one. This one. 45, 38, 31, and 24, and bloop, bloop, bloop. Okay, what happens here? It's linear, so we know it's going to be plus or minus the same thing over and over. We know it's linear because that's what we're doing. That's my only clue. Sorry. What's the difference here? It's minus 7, right? Minus 7. Minus 7 again. Minus 7 again. Okay. So the difference between the terms is negative 7 each time. So we know that our algebraic expression is going to have n times negative 7, right? The further along we go, the more times we'll have subtracted negative 7. We could say n times negative 7. We could also say negative 7 times n, right? Negative 7n. Okay. Now, this is the first term. Yes, this is the first term, second term, third term, fourth term. 1. If we plug in 1 for n, negative 7 times 1, that would be negative 7. Term 1, right? It's not negative 7, it's 45. So what do we need to add to get to 45? We need to add 45 and 7, 52, right? Okay. So my guess is that Tn is going to be negative 7n plus 52. But let's see if we can work with the next term. Term 2, if we plug it into this, 7 times n, 7 times 2, negative 14. The value of the second term is 38. What's the difference there? 14 plus 31. That's also a difference of plus 52. So we found it twice now. I think we can be sure that any term can be found by multiplying the position of the term by negative 7 and then adding 52. Let's see if that works for the fourth term, right? Use this algebraic expression just to check our answer. Fourth term, term 4 equals negative 7 times 4, negative 7 times 4, because n is our term number. Our term number is 4 here, so we plug in 4 plus 52, and this should give us the correct value. 7 times 4 is 28, negative 28 plus 52 equals 24. T4 is 24. Is that true? Yes, it is. So this is the correct algebraic expression. All right, you should be able to do problems with this. Good luck.